you're putting the negative of the other numbers. So if you look at an interval like this one, right here, then those numbers add up to 0. Any interval from the bottom to some element, the numbers add up to 0. Equivalent to the definition.
Equivalent to which definition?
Equivalent to the definition of the Moebius function, that the Moebius function at an element is the negative of the sum of the Moebius numbers underneath.
Right.
That's equivalent to saying that the sum of the numbers in the interval is 0, because the top one is minus the other ones.
Oh.
So an interval means like a quadrilateral? Or?
For example, this is an interval. An interval means you take a bottom element, a top element, and the bottom should be smaller than the top in the poset. And the interval is all the things in between, which in this case are this one, this one, this one, this one, this one. I want to compute a harder example. So what I want to do now is compute the Moebius function for the lattice of flats of my uniform matrix. So the uniform matrix of rank k on n elements. What are the flats here? Well, before I say what the flats is, what is the rank function? So the rank of a set here, basically we know that all the things of size less than or equal to k are independent.
Right.
So if your set has size less than or equal to k, then the rank is just the number of elements. But if the size is bigger than k, then the rank is k. So that means that, what are the flats here? Well,
Flats are sets of elements.
Anything of size up to k minus 1
It's not a flat.
is a flat.
It's a flat.
Is it flat?
You take it and you add anything outside of it, that is
Oh yeah,
the
that's
rank.
right.
Right.
Yeah, but the
But the things of size k and more are not flats because they have rank k, and when you add things to it, they still have rank k.
oh yeah.
So the flats are the sets of size at most k minus 1, and there's another flat,
Everything.
which is everything.
Everything.
So, what does my lattice of flats look like? I have to kind of make a rough sketch here. But the idea is that in the bottom you have the empty set. And then you have how many elements do you have here?
And
You have, on the first floor you have n elements. Each element of the ground set is a flat. So here you have n elements. So you go like this. And in the next floor you have maybe something like this. And how many elements do you have here? Well, any subset of size 2 is a flat. So you have n choose 2. You have n choose 2. Then in the third floor, you have the sets of size 3. 3, and so on. Then in the floor k minus 1, you have all the things of size k minus 1. So there's n choose k minus 1 of them. And then in the very top floor, you have everything. So this is roughly what the lattice of flats looks like, putting a 1 at the bottom. The next thing you do is you put, for each one of these guys, they only cover this 1 at the bottom, so they're all negative ones. Okay. Now let's look at a guy in the second floor. Okay. How many things does it cover?
2.
2, right? Because
Right.
this is a 2-element set, so
Right.
it covers these 2 elements. And it doesn't matter which 2, but each one of these guys covers exactly 2 elements.
Uh-huh.
And so when you look underneath, there's -2 plus 1. So you get a 1. Okay, now, what are you going to see underneath a set of size 3?
The ones in, oh, okay, they're all 1 on that third
You're gonna
tier.
see-
So these are all 1s, right?
Right.
Yeah, okay.
1, 1, 1, 1, 1. They're all 1s.
It's going to cover 3
3 elements.
sets of 2.
Right.
So this guy represents a set of size 3. And so the things underneath it are basically this 3 cube that we drew. So it's going to look something like this.
Yeah.
And so you're going to get 3 1s, 3 negative 1s, and a 1. So that adds up to 1. And you switch the sign, so you get -1. And that's going to be true for any one of these guys. And the same thing goes on and on. So for the 4th floor, you see a 4-dimensional cube underneath. And what do you think you get?
1.
If you believe the pattern that's happening here, 1, -1, 1, -1. It's going to keep doing that. Let's actually prove that. So let's prove that this thing goes 1, -1, 1, -1, and so on. So the way to prove that is basically I'm going to take a guy, let's say on the teeth floor. I'm going to do it by induction. So claim is that the Moebius function, let's say if the Moebius function is -1 to the what? The guys of rank 0 have 1, the guys of rank 1 have -1, the guys of rank 2 have 1, and so on.
Okay,
So I can just say -1 to the rank of x.
Wait, what? Oh, okay.
So if the rank of x is even, like in the floor 0 or 2 or 4, then that's a 1. And if the rank is odd, like in the floor 1 or in the floor 3 or so on, then you get a negative. So that's my claim is that this is my Moebius function. And that might break down in the top level. Because in the top level, it's a little bit different. So I'm going to claim this up to here, up to rank k-1. For the rank of x at most k-1. So what I want to prove is that this thing does alternate between 1, -1, 1, -1, and so on. We'll see that breaks down in the top, but for the other elements it's true. Okay. So prove inductions on the rank of x. So let me take a guy over here and look at the things underneath. So my element here is x. And that's the poset underneath. And so by the induction hypothesis, I can say that these guys are 1s, these guys are -1s, these guys are 1s, -1s, 1s, -1s, so on. Okay. Let's say that this is the kth floor. Okay. So again, the idea is that here I have, in the bottom floor I have n choose 0 guys. In the first floor I have n choose 1 guys. So this is n choose 0. This is n choose 1. No, that's not right. Yeah, that is
That's right.
Yeah.
Yeah.
'Cause, yeah.
Yep.
No, that's not right.
That's right.
Yes.
That's not right because this is part of the bigger poset.
Oh, yeah.
That's
Right,
an
right.
choose.
Right.
Wait.
And so
No,
That's
she's
still
right.
No, didn't you just
Okay.
shrink it down
No.
to the very bottom?
So
But you're not looking at the whole poset, you're looking at,
So what I'm saying is that
Oh,
in
just-
each.
inside here.
right,
Yeah.
right,
There's other guys outside, right?
Sure,
right, right,
sure,
right.
sure, sure.
Oh,
But what I'm saying is that in my interval, in the first floor I have, basically this guy has size k. And so what I'm looking at here is like a k-dimensional cube.
right.
Yeah.
Okay. So in this top floor, I have k choose k guys. In the next floor, I have k choose k minus 1 guys.
Right.
Yeah.
That's true.
Yeah.
And so on. In the bottom, I have k choose 0,
Okay, choose one.
1, k choose 2, and so on. Inside this part.
Uh-huh.
Which is what I care about, because what I want to do is compute the Moebius function of x as the negative of the things underneath.
Uh-huh.
So the Moebius function at x is minus things underneath. But let's see what that is. We're going to add up all these red numbers that we have underneath. So in the bottom floor we have k choose 0 times 1. In the first floor we have minus 1, and we have it k choose 1 times. In the second floor they're all plus 1s, and we have k choose 2 of them. In the third floor they're all minus, and we get k choose 3 of them. So on. So we just get this house creating some plus minus plus minus plus minus, and it ends where?
K choose
At
k
k choose k minus 1.
And it's,
And what's the sign of that guy? Well, we said that it's minus 1 to the rank.
Yeah.
which is k minus one.
So we get this expression. Okay. Does this expression look familiar to you guys?
0.
No?
1 plus negative 1 to the nth is 0.
Right. So what is 1 plus negative 1 to the k power? Well, on the one hand, that's pretty easy because 1 plus negative 1 is 0. So
Uh-huh.
it's 0. But on the other hand, you can multiply this out using the binomial expansion. And you're going to get 1 to the k plus k choose 0, 1 to the k minus 1 minus 1 to the 1, plus k choose 1, 1 to the, this is k to the 1, 1 to the k minus 2 minus 1 to the 2, plus k choose 3, 1 to the k minus 3 minus 1 to the 3, so on until k choose k minus 1, 1 to the 1 minus 1 to the k minus 1, plus k choose k, 1 to the 0 minus 1 to the k. This is k choose 0, 1 to the k, negative 1 to the 0. I don't know if you guys prefer this or you prefer this. The point being that what we have here is actually what we have here.
Mm-hmm.
Just get rid of these ones. 1 to the anything is 1. You don't have to write it down.
Mm-hmm.
And so we get exactly this expression. And so therefore, this is minus this red guy, which is minus 1. So minus k choose k minus 1 to the k. So you get minus 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 1 to the k, which is minus 1 to the k. Which is what you wanted to show. So that shows that my Moebius function is what I'm claiming that it is. Not only for the first floor, but for any floor. So 1, negative 1, 1, negative 1, and so on. Up until here. And then here, this guy is not a cube anymore.
Mhm.
Underneath this guy is the whole poset. So this thing was looking like an n-dimensional cube, and then you kind of truncated it. The point is that underneath this guy, you have all these guys, and when you add up, you just get some number that's not -1 to the k. It's the negative of all these guys. It's a mess, but minus all of this junk. So the Moebius function is very nice except at the top it's a mess, but otherwise it's just ones and negative ones. So that's good when you define an object, in this case a Moebius function, and you find that it behaves well when you look at a nice poset. Okay. So here are 2 examples of Moebius functions, and now the next thing I'm going to do.
Is there a nice formula for that top guy in terms of like n and k?
It's basically minus. It's this garbage basically.
Mhm.
But you can't just say a nice.
There is no nice formula. It's minus
Yeah,
summation
sure.
of
Sure.
n choose I minus 1 to the I from I equals 0 to.
Mhm.
And there's no way of simplifying.
You've chunked it off early. It doesn't do anything
Because
nice.
basically what I did is take this big expression, but this expression is nice because it starts here and it ends at the end. But what I have here is an expression that starts like this and then I chopped it off in the middle. And then there's no nice expression. Okay, so that's another example of a Moebius function, and this should also be helpful when you guys do the homework problem where I ask you to compute Moebius functions. I think the ones that I asked you about in the homework are easier than this one actually. But so what I want to do now is define something else that people. Yeah, question.
Actually, one of them.
Yeah.
Yeah, I think it's actually one of those here.
Okay. Well, if it is, I don't think it is. I think it's very similar, but not quite. Okay. So now let me define. There's 2 things that people call the Moebius function, and there's 2 Moebius functions, one that has 1 variable and one that has 2 variables.
It's my homework.
So the Moebius function what I'm going to do is take a poset and define the Moebius function for a pair of elements x less than y. Okay. So the Moebius function is basically going to be a function that takes in a pair of elements x less than y and assigns an integer. Okay. And what we're going to do is basically the same thing that we just did. So, for example, if you have a bottom element, then the Moebius function of 0y is just mu of y. Okay. And if you want to define the Moebius function of x comma y, then what you do is you just look at the poset above x. And in that poset, you look at mu of y. Okay.
So then you define that, not necessarily finite posets like that too.
Right. So what you do is, let me give you 2 definitions. The first definition is what I just said. So you just look here. You look at the poset of things that are above x. Let's call it p sub bigger than or equal to x. Okay. And y is inside this poset somewhere. And so what you're going to do is just define the Moebius function of x comma y to be the Moebius number of y in this red poset. So in P, the poset of things bigger than or equal to x, you look for y. We put this in red so that you see that this is the red poset I'm talking about here. So this is one way of defining it. Okay. The other way of defining it is just recursively, equivalently. You just say that the Moebius function of x comma x is equal to 1. And if you want the Moebius function of x comma y, then what do? Here's x, here's y. And so what you're going to do is look at this piece right here. And then the Moebius function of x comma y is going to be minus all the things that appear in here. So minus the summation for each z in here Moebius of x comma z.
So z between y and...
For z bigger than or equal to x, smaller than or equal to y in the poset. So this is something that is a little bit more general, but it's not any harder. And note that what I called last time mu of x is mu of the bottom element, comma, x, if you have a bottom element. Okay. Chris? Yeah, that's right. I want a strict inequality here because I'm summing over the things that are between x and y and are not y. Okay. And again, another way of thinking about this is so Chris, you were away when I was pointing out your comment from last time, that another way of understanding this is just if you look at any interval, the sum of the Moebius numbers is equal to 0. So it's equivalent to just sending this to the other side and saying the sum without this strict inequality is equal to 0. The sum of the Moebius numbers in this poset is equal to 0 in the red poset.
Also, so for those two definitions to be equivalent, then you need to say that the bottom guy is 1.
That's what he says.
Yeah, exactly.
That's what I did.
They're equivalent because
Yeah.
you could have multiples of the Moebius function.
Right.
Satisfy that too.
Right. Do you have a question, Eric?
And it's clear if y covers x, what we do, right?
Yeah, so if y covers x, then it's just minus 1.
Sure.
Okay.
And if you don't have a 0 element, it's equal to the Moebius function of whatever is the smallest element under x to x. Is that true?
No.
Not really, because you might have several minimal elements under x.
Yeah.
So I mean, the point is that these Moebius functions you can define for any poset, but generally you only use them for nice posets. And nice posets tend to have zeros, tend to have ones.
Right.
Hopefully, they're often lattices. And when your poset is nice, then you can say nice things about the Moebius function.
Yeah.
For example, here's a nice poset, and you see the Moebius function is nice. There's a whole family of posets for which the Moebius function is ones and negative ones. A lot of posets that we care about have this property.
Federico?
Yeah?
Now, does this Moebius function relate to the Moebius function in number theory, where you sort of invert a sum?
So that's exactly the next thing I was going to say, is that there's a theorem, and this theorem is really the reason why people define the Moebius function. It's called the Moebius inversion formula. Okay. And this Moebius inversion formula is incredibly useful when you're trying to solve a counting problem and there's a poset lying around in your problem. And I'll explain what that means. But for example, well, basically what the Moebius inversion formula says is this. It says, let's say that you have a poset and you have two functions from your poset to whatever, the reals, let's say. It doesn't really matter what you put here. Okay? Now, imagine this. Imagine that you start with your function f. Okay, so your function f assigns to each element of the poset a number. So now you can think of your poset as having a number on each element. And let's say that your function g, what it does is just add up the numbers underneath. Okay? So the function g, what it does is it just looks, here's your poset. Your poset has a bunch of numbers here, you know. Every element of the poset has a number. And these numbers are called f of y, let's say, if this element is called y. And what the function g does is it just says, okay, g of x is summing the things underneath. Less than or equal to.
Oh, f. Oh, okay.
So what g of x does is it adds up all the numbers that you assign to all the things between 0 and x.
So f is any function from p to r?
F is any function from p to r, but in applications usually it's some counting function that says,
Usually z or something.
usually this is z,
But
you know, this could be any ring really.
you have some numbers. Oh yeah, okay. Okay. Yeah.
So
Any group?
any abelian group, yeah, sure. But again, in practice, you know, I actually even want to I just want to put z, because that's what you usually do. But let me just say any other ring will do. But generally, you're counting something. And so actually, generally, you're saying, you know, to each element of the poset, you're counting something. And then g of x just says, you know, you count all the things underneath. What the Moebius inversion formula does is it lets you invert this relation and write f in terms of g. Okay? And it's kind of amazing that the formula is exactly the same, except that you just have a mu of yx there. That's what the Moebius inversion formula says. And
So
What is the f of x formula? So f of x is saying that the number that we assign to x, if f is a counting function, then the number assigned to x is based on the Moebius functions of the things below it, or with?
So I guess one way to think about this is that these Moebius numbers are inevitable because they are the numbers that come up when you try to invert the sum. I mean, very often it happens in combinatorics that when you try to count something, you do have this situation where you have these two functions and they're related to each other. Maybe, let's do an example actually. Yeah. Let's say that you have the I'm going to improvise, so hopefully I won't make a mistake. But divisors of, I don't know, 1,000. Okay. 1,000, 500, 200, 40. I'll draw a poset for you. I have practice, so I know what it looks like, but. Looks like this. 1, 25, 5, 2, 4, 10, 40. No. Yeah, no, 20. 50, 100. Okay. And now let's say that you want to define a function. I don't know yet which one is going to be g and which one is going to be f, but I think this is maybe g. G of d is the number of numbers k between 1 and 1,000 such that they are multiples of k. Such that they're multiples of d, sorry.
So like for 10, you get...
So g of 10 is the number of multiples of 10 between 1 and 1,000.
Okay.
So you get 20, 30, 40, like you count all those guys up to 1,000, right?
Mm-hmm.
Okay.
So f of d is going to be the number of numbers between 1 and 1,000 such that the greatest common divisor of 1,000 and k is d. Okay? So for example, f of 20 is the number of numbers such that the greatest common divisor of 1,000 and k is 20. So for example, what is if a number is a multiple of 100, then what could its greatest common divisor with 1,000 be?
Wait. So g of 100.
So
It could be.
I'm writing something before. I wrote something and I asked you a different question. So the question that I want to ask you is this. Let's look at the numbers that are multiples of 100. and they are between 1 and 1,000.
Right.
Okay? So n is a number such that, or k is a number such that it's a multiple of 100. Then what can the greatest common divisor of 1,000 and k be?
Well, 100 divides both of them.
Could be
100 divides this guy, and 100 divides this guy. So it's at least 100.
Right.
But it could be bigger.
Right.
What else could it be?
Could be k itself.
K itself.
It could be k itself.
Could be
It
something
could be
in between.
some multiple of k.
Some other
Could it be k?
Yeah.
Wait. Sure.
Yeah. Like 500.
Something like 500.
It could be k. Yeah. Whereas I said it wrong actually. I told you this was dangerous when I started improvising, but k is a multiple of 100.
Right.
Yeah.
Like 500.
Okay. No, so then maybe this is not what I want.
Isn't that first thing that you wrote basically just 1,000 over d?
Yeah.
G of d?
Yeah. So d divides k.
That is what we had before, yeah.
Is this true? Is this true that g of 200 is f of 200 plus f of 1,000? So here you have the numbers such that they are multiples of 200.
So you've got 200, 400, 600, 800,
1,000.
and 1,000. So you got 5 of those.
No, I did have it right, I think. So it's either 200, 400, 600, 800, or 1,000.
Yeah.
What could the greatest common divisor with 1,000 be?
Could be 200, 200,
It could be 200
or 1,000.
or 1,000, but it could not be 400.
No.
Right.
So that's why I was confused, because you guys said that it could be k, but it can't necessarily be k.
Can't, not always.
No, but it can.
It could,
In that-
in some
that
cases,
other
it can be k.
example you had, it could have been k.
It can be k. But so this is what I want to say. Okay, now I got it. So the point is, what had I written? I said 100 divides k. So that means that the greatest common divisor of 1,000 and k can be 100.
Could be 500.
It can be 500.
Could be 200.
Be 200.
Could
Could
be 1,000.
be 1,000. But that's it. It couldn't be anything else. Because it's a multiple of 100 and it's divisible by 1,000. So
Thousands of divisible by.
g of 100, the number of things that are divisible by 100, is equal to f of 100 plus f of 200 plus f of 500 plus f of 1,000. The point is that these four guys are the guys that are bigger in the poset. Okay? And that's what you have in general, is that g of d is the summation of f of m for m bigger than d. Okay? Which is the opposite of what I wrote here, but the nice thing about this formula is that actually it works exactly in the same way. If you change these guys,
Okay.
all you have to do is that now x is bigger than y,
Right.
x is less than y, so you get this. Let me just write it out. So the other one says, if g of x is the summation for y bigger than x of f of y, then f of x is the summation for y bigger than x of g of y mu of xy. Which is what I have here. I have the g of d is the summation for m bigger than d of f of m. And so therefore I can apply Moebius inversion and get that f of d is the summation for m bigger than d of Moebius of d comma m g of m. Okay? Now, what is the point here? The point is that I have these two functions that are very closely related to each other, and that one of them is easy to compute and the other one is hard to compute. Which one is easy to compute? G. How many multiples of 100 are there that are less than 1,000? 100, 200, so on. In general, the number of multiples of d less than or equal to 1,000, 1 out of every d of them is a multiple. So this is just 1,000 over d. So it's just 1,000 over m. Okay. And so what I have just computed is a formula for the number of integers between 1 and 1,000 whose greatest common divisor with 1,000 is d. Okay? For example, f of 1 is the bottom element, so I get the summation for m. It might be confusing that I wrote here greater than or equal when this is the order in the poset. So this is the divisor poset, so I should just write here d divides m. I should write here d divides m. I should write here d divides m. And so for f of 1, I just write 1 divides m, but that's nothing. That's every m. And so what you have here is 1,000 over m. And this is the number of integers between 1 and 1,000, such that the greatest common divisor with 1,000 is 1. In other words, they are relatively prime with 1,000. Okay. Have you guys seen this function before? This is called Euler's function phi of 1,000. Okay. This is one of the very important functions in number theory. And if you want to compute it, this is what you do. And if you want to compute it, what you have to do is compute this number. I mean, here you have your formula. This is phi of 1,000. These things are equal to each other. And so if you want your formula for phi of 1,000, you need to compute the Moebius numbers, and then that's how you get your formula. Okay? The formula that you get is that the quantity of numbers which are relatively prime with n is just and are less than or equal to n. It's just n times 1 minus 1 over p1 and so on until 1 minus 1 over pk, where these guys are the primes that divide n. And Sometimes in number theory classes they tell you this formula and they tell you, oh, this is kind of hard to prove, but really the proof just comes from here, and so this is what your question was, is whether this Moebius inversion formula is the same Moebius inversion formula that they use all over the place in number theory. And the answer is that when you apply the Moebius inversion formula to this poset, you get the number theory Moebius inversion formula. If anybody has taken a course in combinatorics and has seen the inclusion-exclusion formula, which I'll tell you what that says. I mean, in combinatorics, a lot of the counting problems that you study say, find the number of objects that satisfy certain properties. So let's say that you have some properties 1, 2, and 3. That an object might satisfy. Okay. And so you might be interested in asking several questions, like, how many objects satisfy properties 1 and 2, but not property 3? These are the kinds of very natural questions that you can ask. And for example, one that you could ask is, how many objects don't satisfy any of the properties? Okay. Question. How many objects satisfy none of the properties? Well, the way that people usually do this is with a Venn diagram, where they say, okay, let's say that these guys satisfy property 1, these guys satisfy property 2, these guys satisfy property 3. So what are we after? We're trying to compute the number of guys that are out here, right, that don't satisfy any of the properties. The way that you answer this question is you say, let's call this E. So you take all of the guys in your set. Okay? And then you say, okay, but they're not allowed to be in 1 or in 2 or in 3. So let's subtract the ones that are in 1. Let's call them maybe the ones that are in set 1. Subtract the ones that are in set 2. Subtract the ones that are in set 3. Now, is that the answer? Well, it's not, right? Because I over-subtracted. For example, these guys that were in groups 1 and 2, first I counted them in E, and I didn't want to do that. So I subtracted them, but I subtracted them twice. Once for being in 1, and once for being in 2. So I over-subtracted, I need to add them. So I need to add them back in. So I add the ones that are in 1 and 2, and for the same reason, I add the ones that are in 1 and 3, and I add the ones that are in 2 and 3. Now am I done? Well, I'm still not done, because now I fixed it for these guys, for these guys, for these guys, but what about the guys that are in all the 3 sets? Then first I counted them, and I didn't want to do that.
Yeah.
I counted them in E, and I didn't want to count them. So I said, okay, I subtract them, but I subtracted them 3 times, because they're in here, they're in here, they're in here. I over-subtracted, and so I decided to add them back in, but I added them back in 3 times. They're here, they're here, they're here, and so that means that I counted them once, subtracted them 3 times, added them 3 times, and so that means I'm still counting them, and I have to subtract them. And then I'm done. Well, so this is how you do it for 3 properties, but in general this works for k properties. And you can imagine what the formula says. Take all the guys, then subtract the ones that have 1 property, then add the ones that have 2 properties, then subtract the ones that have 3 properties, and so on. And what do you think these minus and plus and minus and plus and minus and plus are? They're exactly these red minus and plus that I had here, minus 1s and plus 1s. This is exactly what Moebius inversion says for the poset of the hypercube. So, I mean, the way I stated it sounds like something very abstract that you would never use, but so for divisors, you get the number theory inversion formula. For this poset, I get the inclusion-exclusion formula. And for the lattice of flats of the matroid of a graph, it's your homework to figure out what you get. This is homework 5, problem 5, I guess.
5B and C? A and B?
5A, 5B. I think both of them will work in this way. Okay.
Yeah.
This is an extremely powerful formula that works in many cases, and